Math 2414, trigonometric integrals, integrating a product of sines and or cosines. For those of you currently taking my class, you may notice that I'm not putting the chapter and section number for these videos, and that is actually on purpose. The reason is quite simple. I would like for these videos to be independent of any textbook. So in the event that I change textbooks in the future, or somebody is watching these from Lord knows where using Lord knows what book, they don't have to worry about which chapter and section are you on now, and they can identify it by the topic. Now that being said, I will refer to verbally what those chapters and sections are. For example, if you are currently in my class, or you are using Essential Calculus Early Transcendentals, 2nd edition by James Stewart, then this is chapter 6, section 2. But it's not all of chapter 6, section 2, because in my opinion that section could be split in half. Half of it is trigonometric integrals, the other half is trigonometric substitutions. In my class, I will be treating it as two separate sections. So in your module in Canvas, you'll see 6.2a and you'll see 6.2b. But let's go ahead and continue. Integrating a product of sines and or cosines. On the board, you see two indefinite integrals, and they're exactly the same. Because as I was cleaning up this mess, I forgot to put the square back on that cosine. The first integral is the integral of sine cubed x, cosine x dx, versus the second integral, which is identical except there's a square on the cosine, the integral of sine cubed x, cosine squared x dx. Now, technically speaking, we have the wherewithal to integrate both of these at this juncture. It only requires knowledge that we've already seen, trig identities and substitution. So really what we're going to do, at least for this type of integral, is develop a technique and then apply it. I am going to go ahead and put part 1 up here because I am anticipating this discussion to span at least 4 videos before we shift gears and look at other trig functions. But let's take a look at this first one. This is actually a Calculus 1 integral, assuming that your Calculus 1 class covered integration by substitution. But in my Calculus 2 class, I assume that you have that tool in your arsenal. If we were going to do substitution, I would probably let u equal sine of x for a couple of reasons. Number 1, the sine x has the power on it. Number 2, if u equals sine x, then du is equal to cosine x dx. And it's at this point that I think I'm going to shift gears a little bit. For those who watch the Calculus 1 review videos that I posted, and in my class, that better be all of you, and you were watching the videos about substitution, I mentioned that there were 2 schools of thought on how to proceed here. One school of thought, which is the school of thought that I ran with, was to solve for dx and then substitute that here. But it's hard to break old habits, so I'm going to go back to my original school of thought, which is this. When you're doing an integration by substitution, you need to build what I call the du package. Basically, it's what du is equal to. In other words, instead of solving for dx, I want to build this if it's not already present in the integrand, which it is. Cosine x is already present, dx is already present. So instead of solving this for dx and substituting there and then canceling the cosine x's, I'm just going to encapsulate the entire du package and replace it with the du. In other words, all of this together is just going to become du because that's what du equals. And of course, sine x is going to become u. The only thing not getting changed is the third power, so that will remain when we make the substitution. So our integral becomes the integral of u to the third power. All this becomes du, and this suddenly became really easy. The integral of u to the third power is 1/4 u to the fourth power plus c. It's an indefinite integral. And of course, u is holding the place of sine of x. So our final answer is 1/4 sine to the fourth power x plus c. We could check it easily by taking the derivative, remembering the chain rule and the power rule. The power is on the outside, so it would come down, cancel the 1/4 and get lowered to a 3. Then the chain rule would say times the derivative of the inside, the derivative of sine is cosine, and it would take us right back. Not a big deal. So what's the issue over here? Well, as you can probably imagine, it has something to do with the fact that the power on cosine is a 2 as opposed to an implied 1. Now, could we take the same approach? We could, but here's the problem that will arise. If we let u equal sine of x, then du is equal to cosine of x dx. I've got more cosines than I need in the integrand. In other words, I could rewrite this cosine squared as cosine x, because it is. And when I was taking inventory of the du package needs a cosine x and a dx, which I do have. Those things together would become du. And of course the sine would become u. But who's not accounted for? This cosine. I've got an extra cosine. So what can I do with it? Can I solve this for cosine x? No, don't do that. Just use this to replace the du package with du. I've got a stray cosine. So if I made all my substitutions, the sine cubed x would become u cubed. This cosine x would still be lingering around, and then the other cosine x with the dx together make the du package. And I'm in a pickle here because I'm integrating with respect to u now, and I still have an x. Now, if you're going to really push the envelope and say, well, let me solve this for x by taking arc sine of both sides, substitute that here, that would not be wrong, but I promise you it's going to make the problem, well, it usually makes the problem leagues worse. I'm not going to set up a triangle to draw this, use it to figure out cosine. You know what, I'm going to do it real quick just to see what kind of a mess it makes. Please forgive me. If I wanted to draw a picture of this, u is equal to sine of x, the x is an angle. If I wanted to set up this triangle so its sine was u, sine is opposite over hypotenuse, so u over 1 would give me sine of x equals u. If I did the Pythagorean theorem, I would get 1 minus u squared. And so in this picture, cosine of x is adjacent over hypotenuse, so you would get 1 minus u squared, square root of 1 minus u squared. And then cosine x would become that. Did I make the problem better? Nope. Is it workable? Possibly. But my point is, because of that extra power in the cosine, or because of the power in the cosine, that kind of changed my plan of attack. Plan of attack over here worked really nice. Why? Because the only cosine that was in the integrand was needed to form the du package. Over here, that wasn't the case. So maybe our initial decision at the beginning was not the best choice. So let's go back to this one and make a different decision at the beginning. You can't be afraid to try something, watch it crash and burn, and then go back and try again. It's part of the learning process. Now, when I was a student, I would be like a dog with a bone. I would not let this go. I would push it algebraically and try to force it to work. And I'm not going to lie to you, it will probably work. But I'll be honest, if you gave me that integral that I just erased, the integral of u cubed squared of 1 minus u squared du, and you said do something with it, you know what I would do? We're not there yet, but I would make a trig substitution. I would let u equal sine x and turn it back into this and figure out where to go. So it's like, great, I'm back where I started. But the point I'm trying to make is, when you make a substitution, if you get to a point of no return or you don't know where to move, go back and try a different substitution. Let's clean this up. Well, if we're not going to say u equals sine x, let's restore the integrand. Well, how about u equal cosine x? Well, let's try that and see what happens. Then du is equal to, derivative of cosine is negative sine x dx. Okay, well, you might be thinking, but you're going to be right back in the same situation you were before. And you'd be partially right, except not quite, and you'll see why. All right, so let's focus on building this du package from our substitution. In other words, let's focus on peeling off enough from the integrand to make all this. The dx is already present, that's not a problem. To get the sine x, I would have to borrow one of these. So let's manipulate this a little bit. Let's take off one of the sines, leaving a sine squared x. Leave the cosine squared alone for a second, and take the sine that we borrowed and put it over here with dx. So that this sine x will start helping us build the du package. Now right now the only thing the du package is missing is the minus, or minus 1 if you will. Negatives are easy. You can just drop a negative in there and balance it with an extra negative on the outside. So we still have the same integrand, same integral, we just made it look different so that we could build this du package. So all this will become du. Now what was u? Oh, u is cosine. So cosine of x will become u, but if you'll notice I still have some stray signs. But this isn't the same situation as before. When we did it before, we had a stray cosine. Here we have a stray sine squared. Could I replace that with something that it equals? Well, trigonometrically speaking, what is sine squared equal to using a Pythagorean identity? Well, sine squared plus cosine squared equals 1, which means with this sine squared, we could replace it with 1 minus cosine squared x. Now, is that beneficial? Maybe. If we did replace the sine squared with 1 minus cosine squared x, and we still have this cosine squared x, which is going to become u squared, and we have this negative sine x dx all over here waiting to become du, now everything can be changed. All of this will still become du. You know what, it's bothering me writing u under here because it's really going to become u squared. Same thing over here that was bothering me before. So this will become u squared, but what will this become? Well, since cosine of x is equal to u, then 1 minus cosine squared will become 1 minus u squared. And now our integral is negative integral, parentheses, 1 minus u squared, du, and now that's just a straight up algebra integral. I would distribute the u squared, integrate, don't forget this. We're going to finish this problem in the next video, but the key thing I wanted to point out, and this is what we're going to turn into a technique, is that when you are integrating a product of sines and cosines, you have a couple of choices on what the substitution to be. You can say u equals sine x and u equals cosine x, but not all substitutions are created equal. Here, saying u equals sine x worked because the extra cosine made the du package. Honestly, I could have let u equal cosine x here, said du equals negative sine x, and kind of played the same game I played over there. Whereas on this one, saying u equals sine x kind of backed us into a corner, because when we said u equals sine x, du was cosine x, we borrowed one of these cosines to form the du package and had one left over. But when we said let u equal cosine x and du equals negative sine x dx, we still borrowed one of these, but we had 2 of them left over. And because we had 2 of them left over, we could take advantage of the Pythagorean identity, replace them with some cosines, which we knew what to do with. So what is the driving factor that says we should let u equal cosine instead of letting u equal sine? It's not just who has a power, but who has an odd power. Dun dun dun. That's meant to be a cliffhanger, so check out the next video.